Welcome to the Sleepy Scientist. I'm glad you're here. Whether you're tucked under the covers, curled up on the sofa, or simply letting your thoughts drift like dandelion seeds on a breeze, you're in the right place. In this video, we delve into the fascinating topic of mass and its critical role in our comprehension of the universe. Mass is not just a measure of how much matter an object contains. It is a fundamental property that influences the behavior of everything from the smallest particles to the largest cosmic structures. Understanding mass is essential for grasping the principles of gravity, which governs the motion of celestial bodies and shapes the very fabric of space. As we embark on this journey, we will explore various concepts, including the nature of particles, the forces that bind them, and the cosmic fields that permeate the universe. We will discuss how mass affects gravitational interactions, leading to the formation of galaxies, stars, and planets. Furthermore, we will highlight the significance of mass in our daily lives, from the way we experience weight to its implications in technology and science. By the end of this video, we hope to engage you with the profound importance of understanding mass, not only as a scientific concept but as a key to unlocking the mysteries of the universe and enhancing our everyday experiences. Join us as we unravel the complexities of mass and its implications for both the cosmos and our daily existence. Mass is a fundamental concept in physics that often gets confused with weight, but it is crucial to understand the distinction between the two. Mass refers to the amount of matter in an object, measured in kilograms or grams, and is an intrinsic property that does not change regardless of location. For instance, a 10-kilogram bag of flour has the same mass, whether it is on Earth, the Moon, or in space. Weight, on the other hand, is the force exerted by gravity on that mass and varies depending on the gravitational field strength of the location. For example, the same 10-kilogram bag of flour weighs about 98 newtons on Earth due to Earth's gravity, but it would weigh significantly less on the Moon, where gravity is weaker. This distinction is essential for understanding how objects behave under different conditions. Another important concept related to mass is inertia, which is the tendency of an object to resist changes in its state of motion. The greater the mass of an object, the greater its inertia. This means that a heavier object requires more force to accelerate than a lighter one. For example, pushing a small car is much easier than pushing a large truck, even if both are at rest. This principle of inertia is foundational in physics and has practical implications in various fields, including engineering and everyday activities. In engineering, understanding mass and inertia is vital for designing structures and vehicles. Engineers must consider the mass of materials when calculating load-bearing capacities and ensuring stability. For instance, when designing a bridge, engineers must account for the mass of the vehicles that will travel over it, as well as the forces acting on the bridge due to wind and other environmental factors. Similarly, in automotive design, the mass of a vehicle affects its acceleration, braking distance, and fuel efficiency. Lighter vehicles generally require less energy to move, which is why many manufacturers focus on reducing mass through the use of advanced materials. In our daily lives, the implications of mass are evident in various activities. When we lift objects, the mass determines how heavy they feel and how much effort we need to exert. For example, carrying a backpack filled with books is significantly more challenging than carrying one filled with clothes, even if both bags occupy the same volume. Additionally, mass plays a role in sports and physical activities. Athletes must understand their body mass and how it affects their performance, whether they are sprinting, jumping, or lifting weights. In summary, while mass and weight are often used interchangeably, they represent different concepts that are fundamental to our understanding of physics. Mass is a measure of matter that remains constant regardless of location, while weight is a force that varies with gravity. The concept of inertia, closely tied to mass, explains how objects respond to forces and motion. Understanding these principles has practical implications in engineering, where mass affects design and safety, as well as in our everyday lives, influencing how we interact with the world around us. By grasping the significance of mass, we can better appreciate its role in both the physical universe and our daily experiences. The relationship between mass and gravity is a fundamental aspect of physics that plays a crucial role in our everyday experiences. Gravity, the force that attracts two bodies toward each other, is directly influenced by the mass of those bodies. The greater the mass of an object, the stronger its gravitational pull. This principle is encapsulated in Isaac Newton's law of universal gravitation, which states that every point mass attracts every other point mass in the universe with a force that is directly proportional to the product of their masses. and inversely proportional to the square of the distance between their centers. In simpler terms, this means that larger objects exert a stronger gravitational force than smaller ones, and this force diminishes with distance. To illustrate how mass influences gravitational pull and weight, consider two objects, a small rock and a large boulder. The boulder, having significantly more mass than the rock, exerts a stronger gravitational pull. If you were to weigh both objects on a scale, the boulder would register a much higher weight due to its greater mass. This difference in weight is not just a theoretical concept, it has practical implications in our daily lives. For instance, when we jump, the gravitational pull of the Earth acts on our mass, pulling us back down to the ground. The heavier we are, the more force is required to lift ourselves off the ground, which is why heavier individuals may find jumping more challenging than lighter individuals. Gravity affects objects of different masses in various ways. For example, when you drop a feather and a bowling ball from the same height, you might expect the heavier bowling ball to hit the ground first. However, in a vacuum where air resistance is absent, both objects will fall at the same rate due to gravity. This phenomenon demonstrates that gravity acts equally on all masses, regardless of their weight. In everyday life, we often see the effects of gravity when we observe how different objects fall. A heavy object like a car will accelerate toward the ground just as quickly as a lighter object like a soccer ball, provided that air resistance is negative. This principle is crucial for understanding motion and the behavior of objects in our environment. Understanding gravity in the context of mass is significant for several reasons. First, it helps us comprehend the forces at play in our universe, from the orbits of planets around the Sun to the behavior of objects on Earth. For instance, the gravitational pull of the Earth keeps us grounded, while the Moon's gravity influences ocean tides. Additionally, understanding gravity is essential in fields such as engineering and architecture, where the weight of materials must be considered when designing structures. Engineers must account for gravitational forces to ensure that buildings, bridges, and other constructions can withstand the weight they will bear. Moreover, our understanding of gravity and mass is vital in the context of space exploration. As we send spacecraft to other planets, we must consider the gravitational forces at play. For example, when landing on Mars, engineers must calculate the gravitational pull of the planet to ensure a safe landing. The mass of the spacecraft and the gravitational force of Mars will determine how much fuel is needed for descent and ascent. In summary, the relationship between mass and gravity is a fundamental concept that influences our everyday experiences. Mass determines the strength of gravitational pull and weight, affecting how objects behave in our environment. By understanding this relationship, we gain insights into the forces that govern our universe. From the simplest actions of dropping an object to the complexities of space travel, this knowledge not only enhances our comprehension of the physical world, but also has practical applications in various fields, making it a vital area of study in both science and engineering. Inertia is a fundamental concept in physics that describes an object's resistance to changes in its state of motion, defined as the property of matter that causes it to remain at rest or in uniform motion unless acted upon by an external force. Inertia is directly related to mass. The greater the mass of an object, the greater its inertia, meaning that heavier objects require more force to change their motion compared to lighter ones. This principle is encapsulated in Newton's first law of motion, often referred to as the law of inertia, which states that an object at rest will remain at rest, and an object in motion will continue in motion at a constant velocity unless acted upon by a net external force. To illustrate the concept of inertia in everyday life, consider a scenario involving a passenger in a car. When the driver suddenly accelerates, the passenger feels a force pushing them back into their seat. This sensation occurs because the passenger's body, having a certain mass, tends to remain at rest while the car moves forward. Conversely, when the driver suddenly brakes, the passenger lurches forward. In this case, the passenger's inertia is causing them to continue moving in the direction of the car's previous motion, until the seatbelt or another force acts upon them to stop that motion. This everyday experience highlights how inertia affects our daily activities, influencing how we interact with our environment. Another relatable example can be found in the act of carrying groceries. When you lift a heavy bag, you may notice that it feels much more cumbersome than a lighter bag. This difference in sensation is due to the inertia of the mass you are lifting. The heavier the bag, the more force you need to exert to lift it off the ground. And once it is in motion, you must continue to apply force to keep it moving. If you suddenly stop applying force, the bag will tend to fall back down due to its inertia. This principle is not only applicable to lifting but also to pushing or pulling objects. For instance, Pushing a full cart of groceries requires more effort than pushing an empty one, as the mass of the cart contributes to its inertia. Inertia also plays a significant role in sports, where athletes must understand how to manage their own inertia and that of the equipment they use. For example, in basketball, when a player dribbles the ball, they must exert force to change the ball's direction and speed. The ball's mass contributes to its inertia, meaning that a heavier ball will require more effort to accelerate or decelerate compared to a lighter one. Similarly, in sports like football or soccer, players must account for the inertia of the ball when passing or shooting. A well-timed kick or throw must consider the ball's mass to achieve the desired trajectory and speed. Transportation is another area where the implications of inertia are crucial. In vehicles, engineers must design systems that account for the inertia of the vehicle and its passengers. For instance, when a car accelerates or brakes, the inertia of the passengers can lead to discomfort or even injury if not properly managed. This is why seatbelts are essential. They provide the necessary force to counteract the passenger's inertia during sudden stops or starts. Additionally, in public transportation systems like buses and trains, the inertia of the vehicle must be considered when designing acceleration and braking systems to ensure a smooth ride for passengers. In summary, inertia is a fundamental concept that describes an object's resistance to changes in motion, directly linked to its mass. Through relatable scenarios, such as riding in a car or carrying groceries, we can see how inertia affects our daily activities. In sports, understanding inertia helps athletes optimize their performance, while in transportation, it is crucial for safety and comfort. By grasping the concept of inertia and its connection to mass, we can better appreciate the forces at play in our everyday lives, and the importance of these principles in various fields. Understanding inertia not only enhances our comprehension of motion, but also informs practical applications in engineering, sports, and daily activities, making it a vital concept in both physics and our everyday experiences. The concept of mass in the quantum realm introduces a fascinating and complex layer to our understanding of the universe. Unlike classical physics, where mass is often viewed as a straightforward property of matter, quantum physics reveals that mass is intricately tied to the interactions within quantum fields. In this context, mass does not merely exist as an inherent characteristic of particles, rather, it emerges from the dynamic interplay of these particles with the underlying quantum fields that permeate all of space. This perspective shifts our understanding of mass from a static attribute to a dynamic property that is influenced by the fundamental forces of nature. At the heart of this discussion is the concept of quantum fields, which are the fundamental building blocks of the universe according to quantum field theory. Every type of particle corresponds to a specific quantum field, and these fields exist throughout the universe, even in seemingly empty space. When particles interact with these fields, they can acquire mass through a process known as the Higgs mechanism. This mechanism involves the Higgs field, a specific quantum field that is crucial for explaining how particles gain mass. When particles interact with the Higgs field, they experience a sort of drag that gives them mass. The more strongly a particle interacts with the Higgs field, the more massive it becomes. This interaction is a cornerstone of the standard model of particle physics, which describes the fundamental particles and forces that govern the universe. Virtual particles also play a significant role in the quantum realm, and contribute to our understanding of mass. These particles are not directly observable. Instead, they exist fleetingly as part of the quantum fluctuations that occur in vacuum energy. According to quantum mechanics, even a perfect vacuum is not truly empty. It is filled with virtual particles that pop in and out of existence. These virtual particles can influence the properties of real particles, including their mass. For example, the presence of virtual particles can affect the energy levels of particles, which in turn can influence their mass. This phenomenon is particularly relevant in the context of quantum electrodynamics, where virtual photons mediate the electromagnetic force between charged particles. The interactions with virtual particles and the vacuum energy contribute to the effective mass of particles, illustrating the complex and interconnected nature of mass in the quantum realm. Despite the advancements in our understanding of mass through quantum physics, many mysteries remain. One of the most significant questions is the nature of dark matter and dark energy, which together make up about 95% of the universe's total mass energy content. While we have a solid understanding of the mass of ordinary matter through the interactions of particles and fields, dark matter and dark energy do not fit neatly into our current models. Dark matter, which is thought to exert gravitational effects on visible matter, does not interact with electromagnetic forces, making it invisible and detectable only through its gravitational influence. This raises questions about the nature of mass itself and whether our current understanding is complete. Additionally, the concept of mass in quantum physics raises philosophical questions about the nature of reality. If mass emerges from interactions within quantum fields, what does this imply about the fundamental nature of matter? Are particles truly real, or are they merely excitations of underlying fields? These questions challenge our classical intuitions and invite deeper exploration into the foundations of physics. In summary, the concept of mass in the quantum realm is a complex and evolving topic that reveals the intricate relationships between particles, fields, and forces. Mass emerges from interactions within quantum fields, particularly through the Higgs mechanism, and is influenced by the presence of virtual particles and vacuum energy. Despite significant progress in our understanding, ongoing mysteries surrounding dark matter, dark energy, and the fundamental nature of mass continue to challenge physicists and inspire further research. As we delve deeper into the quantum realm, we uncover not only the complexities of mass, but also the profound implications for our understanding of the universe and the nature of reality itself. This exploration of mass in the quantum context not only enriches our scientific knowledge, but also invites us to ponder the deeper questions about existence and the fundamental forces that shape our universe. The Higgs field is a fundamental concept in particle physics that plays a crucial role in our understanding of matter. It is an energy field that exists throughout the universe, and its significance lies in its ability to provide mass to elementary particles through their interactions with this field. The Higgs field is a scalar field, meaning it has a value at every point in space, but does not have a direction. This field is central to the standard model of particle physics, which describes the fundamental particles and forces that govern the universe. According to the theory, particles acquire mass through their interaction with the Higgs field via the Higgs mechanism, a process that explains how particles that would otherwise be massless gain mass. The Higgs mechanism operates on the principle that particles interact with the Higgs field in varying degrees. When a particle moves through the Higgs field, it experiences a sort of drag that gives it mass. The more strongly a particle interacts with the Higgs field, the more massive it becomes. For example, the W and Z bosons, which mediate the weak nuclear force, interact strongly with the Higgs field and are relatively massive. In contrast, particles like photons do not interact with the Higgs field at all, which is why they remain massless and can travel at the speed of light. This mechanism is essential for the consistency of the standard model, as it allows for a diverse range of particle masses while maintaining the underlying principles of quantum field theory. The discovery of the Higgs boson in 2012 at the Large Hadron Collider at CERN marked a monumental milestone in the field of particle physics. The Higgs boson is an excitation of the Higgs field, and its detection provided experimental confirmation of the existence of the Higgs field itself. The discovery was the result of decades of theoretical predictions and experimental effort, culminating in a series of high-energy collisions that produced the Higgs boson. When the boson was detected, it was found to have a mass of approximately 125 gigaelectronvolts, which aligned with predictions made by the Standard Model. This discovery not only validated the theoretical framework of particle physics, but also opened new avenues for research into the fundamental nature of mass and the universe. The implications of the Higgs boson discovery extend beyond the confirmation of the Higgs field. It has profound consequences for our understanding of the universe's structure and evolution. The Higgs field is believed to have played a critical role in the early universe, particularly during the process of cosmic inflation. Shortly after the Big Bang, the universe underwent a rapid expansion, and the Higgs field may have contributed to the mass of particles, allowing for the formation of atoms, stars, and galaxies. Understanding the Higgs field and its associated boson helps physicists explore the conditions of the early universe and the mechanisms that led to the formation of the cosmos as we know it. Moreover, the Higgs field is connected to broader questions about mass in the universe. While the Higgs mechanism explains how elementary particles acquire mass, it does not account for all forms of mass. For instance, the mass of composite particles, such as protons and neutrons, arises not only from the Higgs field but also from the strong nuclear force that binds quarks together within these particles. This distinction highlights the complexity of mass in the universe and the interplay between different forces and fields. Additionally, the Higgs field raises intriguing questions about the nature of mass itself. If mass is a result of interactions with the Higgs field, what does this imply about the fundamental nature of matter? This inquiry leads to deeper philosophical considerations about the essence of reality and the forces that govern it. The Higgs field challenges our classical intuitions about mass and invite us to reconsider our understanding of the universe's fundamental components. In summary, the Higgs field is a pivotal element in particle physics, providing mass to elementary particles through the Higgs mechanism. The discovery of the Higgs boson at CERN confirmed the existence of this field and validated the theoretical framework of the Standard Model. Implications of this discovery extend to our understanding of the universe's structure, the conditions of the early cosmos, and the nature of mass itself. As physicists continue to explore the mysteries of the Higgs field and its role in the universe, we gain deeper insights into the fundamental forces that shape our reality and the intricate relationships between mass, energy, and the cosmos. The ongoing research surrounding the Higgs field not only enhances our scientific knowledge, but also invites us to ponder the profound questions about existence and the nature of the universe. This exploration of the Higgs field and its significance in providing mass to particles is a testament to the remarkable journey of human understanding in the quest to unravel the mysteries of the universe. Dark matter is one of the most intriguing and elusive components of the universe, playing a crucial role in our understanding of cosmic structure and dynamics. Defined as a form of matter that does not emit, absorb, or reflect light, dark matter cannot be observed directly through electromagnetic radiation. Instead, its existence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Comprising approximately 27% of the universe's total mass energy content, dark matter is a significant player in the cosmic landscape, influencing the formation and behavior of galaxies and galaxy clusters. The significance of dark matter in the universe cannot be overstated. Its presence is essential for explaining various astronomical phenomena that cannot be accounted for by the visible matter alone. For instance, observations of galaxy rotation curves reveal that stars in the outer regions of galaxies rotate at much higher speeds than would be expected based solely on the gravitational pull of the visible matter. According to Newtonian physics, the outer stars should orbit more slowly, similar to planets in our solar system. However, the observed velocities suggest that there is much more mass present than what we can see, leading to the conclusion that a substantial amount of unseen mass dark matter must. Dark matter also plays a pivotal role in the formation of galaxies and the large-scale structure of the universe. In the early universe, shortly after the Big Bang, matter was distributed relatively uniformly. However, small fluctuations in density allowed gravity to begin pulling matter together. Dark matter, with its gravitational influence, acted as a scaffolding for the formation of galaxies. As dark matter clumped together under its own gravity, it created potential wells that attracted ordinary matter, leading to the formation of stars and galaxies. This process is crucial for understanding the hierarchical model of galaxy formation, where smaller structures merge to form larger ones over cosmic time. The influence of dark matter extends beyond individual galaxies to the large-scale structure of the universe. Observations of galaxy clusters and the cosmic microwave background radiation provide evidence for the existence of dark matter. Gravitational lens, a phenomenon where light from distant objects is bent by the gravitational field of massive foreground objects, allows astronomers to map the distribution of dark matter in galaxy clusters. By studying how light is distorted, scientists can infer the presence and distribution of dark matter, revealing that it is not evenly spread but rather concentrated in specific regions, influencing the overall structure of the universe. Despite its significant role in the cosmos, the nature of dark matter remains one of the most profound mysteries in modern astrophysics. Numerous candidates have been proposed to explain dark matter, with the leading theories suggesting that it is composed of weakly interacting massive particles, axions, or stereoneutrinos. These hypothetical particles would interact very weakly with ordinary matter, making them difficult to detect. Various experiments are currently underway to search for direct evidence of dark matter particles, including underground detectors designed to capture WIMPs and particle accelerators that aim to produce dark matter candidates. The ongoing search for understanding dark matter's nature is a multifaceted endeavor that involves both theoretical and experimental approaches. Scientists are exploring various avenues, including astrophysical observations, particle physics, experiments, and cosmological simulations. The Large Hadron Collider at CERN is one of the key facilities, investigating potential dark matter candidates by colliding particles at high energies to create conditions similar to those in the early universe. Additionally, Observatories such as the Vericy-Rubin Observatory, set to begin operations soon, will conduct large-scale surveys of the night sky, providing valuable data on the distribution of dark matter and its effects on galaxy formation. Moreover, advancements in technology and computational methods are enhancing our ability to simulate the behavior of dark matter in the universe. By creating detailed models of cosmic structure formation, researchers can compare simulations with observational data to refine our understanding of dark matter's properties and its role in shaping the universe. These simulations help to visualize how dark matter interacts with ordinary matter and how it influences the dynamics of galaxies and galaxy clusters over time. In summary, dark matter is a fundamental component of the universe, defined by its gravitational effects rather than its electromagnetic interactions. Its significance lies in its ability to explain phenomena that cannot be accounted for by visible matter alone, influencing galaxy formation and the large-scale structure of the cosmos. The ongoing search for understanding dark matter's nature involves a combination of theoretical exploration and experimental investigation, as scientists strive to uncover the properties of this mysterious substance. As we continue to probe the depths of the universe and refine our understanding of dark matter, we move closer to unraveling one of the most profound mysteries in modern astrophysics, shedding light on the fundamental nature of mass and the forces that shape our universe. The quest to understand dark matter not only enhances our knowledge of the cosmos, but also challenges our perceptions of reality, inviting us to explore the unknown and expand the boundaries of human understanding. The relationship between mass and the flow of time is a profound aspect of Albert Einstein's theory of general relativity, which revolutionized our understanding of gravity and its effects on the fabric of space. One of the key concepts that emerges from this theory is gravitational time dilation, which describes how time passes at different rates in varying gravitational fields. According to general relativity, the presence of mass warps the space-time continuum, causing time to flow more slowly in stronger gravitational fields compared to weaker ones. This phenomenon has far-reaching implications, not only for our understanding of the universe, but also for practical applications in technology and our everyday experiences. Gravitational time dilation can be understood through the lens of Einstein's theory, which posits that gravity is not merely a force acting at a distance, but rather a curvature of space-time caused by mass. When a massive object, such as a planet or a star, is present, it creates a gravitational well that affects the flow of time. The closer an observer is to a massive object, the more pronounced the effects of gravitational time dilation become. This means that time will pass more slowly for someone situated near a massive object compared to someone who is farther away from it. The implications of gravitational time dilation are significant and have been confirmed through various experiments. One of the most famous experiments involved atomic clocks placed at different altitudes. In a study conducted by the National Institute of Standards and Technology, 2 highly accurate atomic clocks were synchronized and then one was placed at sea level, while the other was taken to a higher altitude. After a period of time, the clock at sea level, which was closer to the Earth's mass, recorded slightly less time than the clock at a higher altitude. This experiment demonstrated that time indeed flows more slowly in stronger gravitational fields, confirming the predictions of general relativity. To further illustrate how mass influences time in different gravitational fields, consider the example of black holes. Black holes are regions of space where gravity is so intense that nothing, not even light, can escape their grasp. As one approaches the event horizon of a black hole, the gravitational field becomes extremely strong, leading to extreme time dilation. For an observer falling into a black hole, time would appear to slow down dramatically relative to an observer far away from the black hole. From the perspective of the distant observer, the infalling person would seem to take an infinite amount of time to reach the event horizon, while for the person falling in, time would continue to pass normally. This stark contrast highlights the profound effects of mass on the flow of time in extreme gravitational environments. Another example can be found in the context of the Earth and its gravitational field. The difference in gravitational time dilation between the surface of the Earth and a satellite in orbit is measurable and has practical implications for technologies such as the Global Positioning System. GPS satellites orbit the Earth at an altitude of about 20,200 kilometers and experience a weaker gravitational field compared to clocks on the Earth's surface. As a result, the clocks on the satellites run slightly faster than those on the ground. To ensure the accuracy of GPS positioning, engineers must account for this time dilation effect, adjusting the satellite clocks to synchronize with those on Earth. Without these corrections, GPS calculations would quickly become inaccurate, leading to significant errors in positioning. The relationship between mass and time also connects to everyday experiences in more subtle ways. For instance, consider the experience of traveling to a high-altitude location, such as a mountain. As one ascends, the gravitational field weakens, and time flows slightly faster compared to being at sea level. While the difference is imperceptible in daily life, it serves as a reminder that our perception of time is influenced by the gravitational environment we inhabit. Similarly, the effects of time dilation become more pronounced in scenarios involving high speeds, as described by special relativity. When objects move at speeds approaching the speed of light, time also dilates, leading to scenarios where time passes differently for observers in motion compared to those at rest. In summary, the concept of gravitational time dilation illustrates how mass affects the flow of time in the context of general relativity. The presence of mass warps the fabric of spacetime, causing time to pass more slowly in stronger gravitational fields. This phenomenon has been confirmed through experiments and has significant implications for our understanding of the universe, as well as practical applications in technology such as GPS. By exploring the relationship between mass and time, we gain insights into the nature of reality and the intricate connections between gravity, motion, and our everyday experiences. The effects of gravitational time dilation serve as a reminder that time is not a fixed entity but rather a dynamic aspect of the universe, influenced by the mass and energy present in ourselves. As we continue to explore the mysteries of the cosmos, the interplay between mass and time will undoubtedly remain a central theme in our quest to understand the fundamental nature of reality. This exploration not only enriches our scientific knowledge, but also invites us to reflect on the profound implications of time and gravity in our lives, challenging our perceptions and expanding our understanding of the universe. In this video we have explored the multifaceted concept of mass, delving into its significance and implications across various domains of physics and our everyday lives. We began by defining mass as a fundamental property of matter, distinguishing it from weight, and highlighting its role in understanding the universe. We discussed how mass is not just a static attribute but a dynamic property that emerges from interactions within quantum fields, particularly through the Higgs mechanism. This mechanism explains how particles acquire mass and is central to the standard model of particle physics. We then examined the relationship between mass and gravity, introducing the concept of gravitational time dilation, as described by Einstein's theory of general relativity. We learned that mass warps the fabric of spacetime, causing time to flow more slowly in stronger gravitational fields. This phenomenon has profound implications, as demonstrated through experiments and real-world applications, such as the functioning of GPS technology. We also touched on the significance of dark matter, which constitutes a substantial portion of the universe's mass and influences the formation of galaxies and cosmic structures. Throughout our discussion, we emphasized the interconnectedness of mass, gravity, and time, illustrating how these concepts shape our understanding of the universe and our experiences within it. The exploration of mass extends beyond theoretical physics. It invites us to reflect on the nature of reality and the fundamental forces that govern our existence. As we conclude this video, we encourage you to engage with the content further. If you've found this exploration of mass and its implications intriguing, please consider subscribing to our channel for more insightful discussions on related topics. Your support through likes and shares helps us reach a broader audience and fosters a community of curious minds, eager to learn more about the wonders of the universe. Additionally, we invite you to explore related content on our channel or website. There you will find a wealth of resources, including videos, articles, and discussions that delve deeper into the concepts we've touched upon today. Whether you're interested in the intricacies of quantum physics, the mysteries of dark matter, or the implications of general relativity, we have something for everyone. Your engagement is vital to our mission of spreading knowledge and fostering curiosity. We encourage you to leave comments, share your thoughts, and ask questions about the topics we've discussed. Your insights and inquiries not only enrich our community but also inspire future content that addresses your interests and curiosities. Thank you for joining us on this journey through the fascinating world of mass, gravity, and time. We look forward to continuing this exploration with you and uncovering more of the universe's mysteries together. Remember, the quest for knowledge is a shared adventure, and we are excited to have you as part of our community. Don't forget to subscribe, like, and share, and let's continue to explore the wonders of the cosmos together.